So now again we will be going for the p-type semiconductor. And so what we can say in this p-type semiconductor, that in p-type semiconductor we will be having the electrons as a minority charge carrier and the hole as a majority charge carrier. So again I will be using a subscript P, capital P. So I'm, for the sake of convenience, so I will be referring as a capital P. So I'm writing N capital P and P P. Okay. So when we are writing NP, we are seeing it as a minority charge carrier concentration. So we are seeing that holes are more in the p-type semiconductor. So the electrons that are available in the p-type semiconductor are less. Therefore, PP are the majority charge carrier concentration and P is the minority charge carrier concentration. We can write the properties as we have written for the n-type semiconductor. So these majority and minority charge carrier present in the p-type semiconductor are also known as the mobile charge carrier. So when we are referring it to a mobile charge carrier, what we are saying that they are free to move. And when we are saying they are free to move, that means we are saying that they will going to cause the conduction in a semiconductor. So it will going to cause a conduction. Now we can write here that PP will be much greater than NP, because we are talking with respect to the p-type semiconductor. So we have already seen that in the p-type semiconductor we are talking about the acceptor. Okay, so here we will be talking about the Na, which is known as the acceptor ion concentration, and this is due to group 3. So I'm writing it as a acceptor ion concentration, and this is due to group 3. And again, when we are talking with respect to the properties of it, as we have discussed for the n-type semiconductor, we again say these acceptor ion concentration are immobile charge carrier. And when we are referring to the immobile charge carrier, that means they are not free to move. So I'm writing it, they are not free to move. And when we are saying they are not free to move, we are saying so they do not cause any conduction. And we can say that Na is roughly equal to Pp. This is the important properties. Now we will be talking about the conductivity in the p-type semiconductors. So when we are talking about the conductivity in the p-type semiconductor, we write sigma p equal to E and P mu n plus E pp mu p. And now if you remember that electrons are the minority charge carrier, that means Np, we are referring it, these are the minority charge carrier. So we can write this E and P mu n, the conductivity due to this will be considered as very low. So I'm writing it as a minority charge carrier. So we can write sigma P equal to E pp into mu p. Its unit is Siemens per meter. Siemens per meter. And now we will be talking about the resistivity. So the resistivity is defined as a reciprocal of the conductivity. So we can write rho equal to 1 by sigma p. So I'm writing rho p equal to 1 by sigma p, and this is equal to 1 by E and A mu p. Okay, because we know that this Na is equal to Pp, acceptor ion concentration, and its unit is ohm meter. Now we will be talking about the current density J. So I'm writing current density J. So again, current density J is been defined as the sigma p into E. So I'm writing Jp equal to sigma p into E, and this is equal to E and A mu p into E. Its unit is ampere per meter square. Now, according to the mass action law, you remember Np equal to Ni square. So we will be writing here Np multiplied by Pp equal to Ni square. And now here we are talking with respect to the minority charge carrier, that is Np. Okay, so I will be writing Np equal to Ni square by Pp, and this Pp is equal to Na. So I can write this equation as Ni square by Na. So this equation refers to the minority charge carrier concentration. So I'm writing here, this refers to the minority charge carrier concentration.